Hello everyone. Thanks to everyone for watching this video. My name is Qidang. I am an architect and engineer. Today's video is titled Structural Fire Engineering, and it is going to provide you fundamentals of structural fire engineering and also the interpretation for the World Trade Center collapsing. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the topic, and then focus on the membrane action and the World Trade Center collapsing before wrapping up with conclusions. Okay, what is structural fire engineering? If you have a fire load which is similar to a structural load that you may consider you've got your loading scenario, then you do heat transfer that you understand how your structure heats up, and then you can perform a structural analysis to understand the response of your structure at elevated or high temperature. So you have fire, your heat transfer, and your structural analysis. This is actually the aftermath of the big test. It was a really dirty fire and really hot. What came out of the test were some really interesting observations, because clearly these composite slabs of standing up, they should have failed, and so there was a bit of head scratching going on. Finally, came up with the fact that the slabs were holding the beams up. This is a very simple sort of station of the way slabs behave in fire. There is a slab initially you start heating things. You heat the beams underneath, you heat the slabs on top, which heat slower thermal expansion dominates. The slab tries to expand against this environment, therefore causes massive compressions, probably buckles itself down lows a bit. But basically, it is pushing against its environment as temperatures go up. And they keep going up, certainly, in terms of that test. Everything reverses in the end. The steel weakening gets so much a dominant effect that the slab is actually hanging there. So the middle of the slab is now in a sort of uniform tension. The wonderful thing that can happen is that provide the edge beams. The boundaries of the slab are kept fairly close to where they were originally in the vertical sense. You get this rather wonderful ring of compression around the outside. The whole thing works a bit like a bicycle wheel. Bicycle wheel's tension spokes compression rim, and it's all itself equilibrating. All you've got to do, if you can achieve this tensile membrane action, is to provide the vertical support around the outside. This is an intermediate approach that I'm going to deal with now. Just one thing to start with is to illustrate this point about having to support the slab vertically. I always think of the way the slab behaves a matter of whether you can do origami with it. Can you fold it? If one of your beams actually is capable of collapsing, folding plastically in the fire, then in order to hold that slab up, you've actually got to have a whole load of horizontal restraint forces from the surrounding structure that doesn't work very well, obviously, for edge base of your building. So this is what we call catenary action. It is a fairly dodgy thing to rely on. This is what happens when tensile membrane action really works for you. You are supplying the required vertical support around the edges. The middle of the slab goes into a nice tension, and the concrete itself around the outside of maybe the edge beams themselves, which are composite, carry this balancing ring of compression. That is what both these methods are actually based on. So, some very simplified concepts: what happens when a structure heats up, consequence of failure. We start with beams, simplifying the diagram shown there. If I heat a beam up, then it's going to start to feel gas hot that expands. In this case, you might see some sort of deflection. It may start to fall down, but it doesn't necessarily mean it's going to collapse. Sometimes, a large degree of deflection can actually be caused at high temperature. It doesn't matter where it could be high in the building or low down. The scenario is pretty much the same. However, if the thermal expansion or contraction forces are too great, then we could lose the joint. The joint could collapse and give way in that situation on the right-hand side that you see there. You then have a tall column which is unsupported over a large length, and that's at the risk of buckling failure. Columns are a lot more critical. If we have a buckling which impacts the column to the point where it is going to lose structural stability. The case of the World Trade Center disaster is an example to illustrate this progressive collapse and to get you thinking. The terrorist attacks on the World Trade Center resulting in it collapsing with surprising ease. More than 2,700 people died. In the case of the World Trade Center, the collapse was due to the design of the building. They have very stiff beams because they were very long beams spanning right from the lift core in the building out to the perimeter columns. So, you didn't have internal columns that are going to compromise the ability to rent floor space. The impact of the aircraft itself would have knocked the fire protection off. And so, when you got expansion of those beams in fire, they push against the very flexible columns and knock the columns out of alignment, and eventually that leads to the collapse. As a result, of course, they don't design buildings that way anymore. Fire research found that using less rigid steel beams supported by columns at regular intervals was preferable. The beams buckle and say, but the columns hold them in place. We've shown that because you get this sagging taking place, which can be up to 30% of the cost of the steel works, so that is very substantial. We have to make sure that the connections are robust enough. When you've got the fire acting on the structure to be able to hold that beam in place, so you don't get failure. It keeps the fire in a compartment and it allows the occupants to get out of the building. From conclusions, what we learned: the structural fire safety engineering requires an understanding of structural behavior in fire. Tensile membrane action can greatly increase the fire resistance. As one of key elements, columns support slab and beams, so its failure due to heating and increased length caused by joint failure may be disastrous. In the case of the World Trade Center, the long span beam was subjected to high transverse horizontal shear, but it was designed only for vertical shear. When the beam collapsed, then increase length of columns and make a disaster. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.